Okay, so they're functions. Let's go ahead and look at a really easy example of kind of working through the whole process about functions and their inverses. The function that I would like to look at, this means suppose an s with the p hanging from it, is suppose we're looking at the function f of x is equal to x plus 1. So let's start through the whole process. First of all, does this function f of x equal x plus 1 have an inverse? Well, we have two ways to check for this. Remember, we have the calculus approach and we have the graphical approach. So first of all, let's go ahead and look at the graphical approach. This is easy. This is a nice little line, y-intercept of 1, slope of 1. So there's my graph of my line y equal x plus 1. Well, it passes the horizontal line test. Therefore, it has an inverse. So that's one way that we could look at this. Another way that we could look at this is using calculus, which of course is cool. So the calculus approach would be to look at this in terms of the derivative. The derivative of x plus 1 is easy enough. It's just 1. So this is f prime of x here is 1, which is always positive. Therefore, this graph, the graph of x plus 1, is monotonic increasing. And we can see that from up above when we actually graph this function. It's always increasing. It will never decrease. It's always increasing. That's what this is referring to. So since it's monotonic increasing, an inverse exists. That's exciting. So we know an inverse exists. So the question is, now that we know the inverse exists, what does it look like? Well, the easiest way to determine what it looks like is to swap the domain and the range. So we're going to do this point by point. Now, this is easy to do with a line, but it's not so easy to do if we get a pretty complicated function, but it still can be done. So let's go ahead and look at swapping the domain and the range. First of all, we have the function f of x equals x plus 1. And let's go ahead and look at some plotted points. Here's my domain, x is my domain, here's my range. So some values I could plug in are -1, 0, 1, and 2. Those are easy values. If I plug a -1 into my function, I come up with -1 plus 1, which is 0. 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. So that's my original function. Now, the domain of my inverse will be the range of my original. Now, I'm not exactly sure what my inverse function looks like quite yet in terms of x's and y's. So again, the domain and the range swap. So all of these values, -1, 0, 1, 2, become the y values over here. So let's look at this ordered pair, -1, 0. This becomes 0, -1. 0, 1 in my original function becomes 1, 0 in my inverse function, and similarly with my other two values. So next we want to go ahead and look at the graphs here. Okay, so what I did is I went through and I graphed each of these functions. This function in blue, f of x, is equal to these values over here plotted. These values in red for my inverse is equal to this line right here. The green dotted line right here is the line y equal x, and we can see pretty clearly that it does reflect across the x-axis. So I found out that an inverse exists. I found out what the inverse looks like by swapping the domain and the range. So the third thing I'm going to look at now is to actually trying to figure out what function describes this inverse. Now this example is pretty easy because I can just go up here and look at this graph and think, okay, this is an equation of a line. Okay, it's a line. The slope is rise 1, run 1. So the slope is 1 times x. My y-intercept is a -1. So this is just the equation x minus 1. That's my inverse. So this is really easy. By inspection, I can determine that. So again, I know that the function has an inverse. I know what it looks like from the graph of above. Now, what is that function? Well, we can just look at this by inspection of the graph and see that it is f inverse of x is equal to, what did we decide? X minus 1. But now the question is, how would I do this for a more complicated function? Is there an algorithm or a series of steps that I can follow to see what's going on here? So let's go ahead and look at the steps that we would usually take. Usually we can't just look at something by inspection and figure out what to do. The first step is to solve for x as a function of y. And then after we've solved for x as a function of y, I interchange the variables x and y. Now sometimes the first step isn't even possible. I know a function has an inverse, but I can't solve for x as a function of y, and I'm done. I can't really do much else than that. So let's go ahead and look at our example. So for our example, we had y equal x plus 1, and then step 1 said to solve for x as a function of y. So that means I want x equals stuff only with y's on the other side and constants. So if I solve for x here, I get y minus 1. The second step is to interchange. So everywhere I see an x, I put a y, and everywhere I see a y, I put an x. So this is f inverse of x. And what's really nice is it's exactly what I thought it would be by inspection. So this worked out pretty slick. Now again, not all the time can I do this. Sometimes I'll run across a function where I cannot solve for x as a function of y. So fourth step, how do I know if I got it right? In other words, how do I know if the function and the inverse that I found are actually inverses of each other? Another way we could talk about this is how to check if two functions are inverses of each other. So the way we can check is to look at composite functions. The rule is a function g is the inverse of f if both of the following hold true. F of g of x is equal to x, and g of f of x is equal to x. And there's one more caveat we need to put here. For each x in the domain of g, and for each x in the domain of f. And this will come into play a lot with square root functions. So let's go ahead and check the functions we found. We had f of x equals x plus 1 as our original. And then we're also given f inverse of x that we determined was equal to x minus 1. So f of x, our original function, is x plus 1. And remember, sometimes we denote f inverse as g of x. Okay, so that's what they're using for this notation. So let's go ahead and check f of g of x. This means in my function f up here, right here, everywhere I see an x, I plug in this entire function in for that. So I'm going to get x minus 1, that's my g of x, and then this plus 1 comes from my f of x. And when I do that, I get x, so this is good. Next thing we want to check is g of f of x. Okay, this is going to be similar. Everywhere in my function g, where I have x in my function g, I'm going to put an x plus 1. Minus 1 comes from my original function, and that checks. So therefore, they are inverses of each other. And that's very exciting. But again, this is a pretty easy example. You'll be looking at some pretty neat algebra stuff here when you're trying to solve for these.